Hello everyone. In this video, I'll be giving you a detailed code walkthrough of my smart wearable fitness band project, the FitBand. This is an IoT device I developed that combines step tracking, visual feedback through RGB LEDs, audio notifications, and Bluetooth low energy connectivity. We will now dive into how the code brings this fitness band to life. So, at the start, at the top of our code, we have the import statements. I'm using MicroPython, which is perfect for the embedded systems like this. So first we have the essential libraries, so machine for hardware control, time for delays in timing, struct for packaging binary data, and NeoPixel for controlling the RGB LED strip. For Bluetooth functionality, I'm importing Bluetooth and UBINASCII for binary to ASCII conversions. The BLE advertising module helps create proper BLE advertisement packages. And then finally, I'm using const from MicroPython to define memory efficient constant. These imports give us everything we need to interact with the sensors, LED speakers, and the wireless communication. So now we'll look at the heart of the step tracking, which is the accelerometer class. This interfaces with the BMI 160 sensor via I2C communication. In the constructor, I store the I2C interface, then immediately configure with the BMI 160 by writing to register 0 by 7E with the value of 0 by 11. This puts the sensor into normal active mode, so it can start detecting motion. Next, I set up at pin 11 as an input with a pull-up resistor. This is crucial. The BMI 160 will trigger this pin when it detects a step. I configure an interrupt on the falling edge, which calls our step interrupt handler method. This interrupt-driven approach is more efficient than just constantly polling the sensor. And then we initialize our step count at 0. The readX method demonstrates I2C communication. We read 2 bytes from the register 0 by 12, which contains the x-axis acceleration data. Using the strut unpacked with the format less than h, we convert these raw bytes into a signed 16-bit integer. The less than sign indicates the little endian byte order. The enable step interrupt method is where we configure the BMI 160's built-in step detection algorithm. First, we register with the 0 by 52 with bit 3 set to enable the step detection feature. Then register 0 by 53 with bit 3 set to enable the INT1 output pin on the sensor. Then finally, we register the 0 by 55 with bit 0 set routes the step detection interrupt specifically to the int1 pin, which connects to our GPIO pin 11. The step interrupt handler is very simple. It just increments our step counter. Because this runs on an interrupt, it executes immediately when the sensor detects a step, ensuring that we never miss a count. Next is the button interrupt class. So this is our user interaction with the button IRQ class. This handles the button press to switch between the different display modes. So in terms of initialization, we configure a GPIO pin as an input with a pull-up resistor. This means the pin normally reads high, and pressing the button connects it to ground, creating a falling edge. We attach an interrupt to this falling edge that calls our handler. To initialize, 2 important variables, last toggle for debouncing and button event as a flag for the main route. Here is our interrupt handler. It's where the debouncing happens. When the button is pressed, we check if at least 250 milliseconds has passed since the last press. This prevents mechanical switching bounce from registering multiple presses. If enough time has passed, we update the timestamp and set the button event flag to 1, signaling the main loop that the user has pressed the button. Next is our Bluetooth functionality, and this is what makes our fitness band an IoT device. So firstly, I defined the BLE constants, the IRQ central connect for when a phone or device connects, and the IRQ central disconnect for when it disconnects. The characteristic flags flag read and flag notify determine how BLE characteristics can be assessed, readable by connected devices, and able to push notifications. I create a custom BLE surface with UUID here. This uniquely identifies the fitness band service. So under this service, I have 3 characteristics. The step count characteristic, which is our characteristic for broadcasting our step data. The LED status, so this is our LED characteristic to show activity level. And then our step count goal, our goal status characteristic to indicate when the user has achieved their step goal. Each characteristic has both read and notify permissions, meaning the device can request the current value or receive automatic updates. So in our class initialization, in the constructor, we activate the BLE hardware and register our custom service and get handles for each characteristic. These handles are how we reference characteristics later. I initialize an empty set to track connected devices and create an advertising payload with our device name FitBand and then service the UUID, then start advertising. The update goal status is at 0, which call initializes the goal achievement flag. Then we have the event handler. So the underscore IRQ method handles connection events. When a central device connects, we add its handle to our connection set. When it disconnects, we remove it and restart advertising so other devices can connect. Then we have our update methods. So we have 3 update methods handle broadcasting data. So each of the following follows the same pattern. So pack the data using the struct pack, and then we write it to the characteristic, and then notify all the connected devices, as you can see. For steps, we use the less than large H format, an unsigned 16-bit integer allowing up to 65,535 steps. For the LED and go status, we use the less than B format, a signed byte, which is efficient for our small numeric codes. This device and design means any connected smartphone app receives real-time updates automatically. So let's look at the helper functions that create the fitness band sensory feedback. So here we have our red flash for high intensity. It flashes red 10 times by alternating between red at a brightness of 80 and off when configurable delays. This gives the user immediate visual feedback during the high intensity. Next, we have our play tone. So this is our audio feedback mechanism. We create a PWN signal on the speaker at a specified frequency, and then we set our duty cycle to 50%, which creates a clear tone. And then after the duration, we stop the PWM and de-initialize the pin to free up resources. This function is the foundation for most of our sounds. And then we have our celebrate goal. So when it flashes yellow, when the user reaches their step goal, we want them to feel accomplished. So we give them a yellow flash 6 times, conveying the achievement. Play a 3-note ascending melody at 800 hertz and 1000 hertz and 1200 hertz. So the increasing pitch and the longer final note creates a satisfying victory noise. Next, we have our boot up sound. So on startup, we have a 4-note ascending sequence that just gets progressively longer. This tells the user their device is initializing successfully, and it's a small detail that makes the device just feel more natural and polished. Then we just have the shutdown sound. So the opposite of the boot up, 3-note descending sequence provides audio confirmation when the user stops the device. Next, we have our main function where everything sort of comes together here. So first, we initialize the I2C components on pins 20 and 21 for our accelerometer communication. I create our accelerometer instance and enable step detection interrupts. The button is set up on pin 9. Our NeoPixel RGB LED strip with 3 LEDs is on 7, and we initialize it to white. The BLE device is created with the name FitBand, and then pin 16 controls the speaker, and pin 22 is the status LED that turns on, that shows the device is running. So next is our configuration variables. So I define the activity detection window as 5 seconds. So this is how we recalculate the activity level. It's purely just for the demonstration purposes. It can change this however long for the specific user. The thresholds are 2 steps for inactive, 6 steps for moderate, and anything above is high intensity. So very quick steps, very intense activity. Then the goal for the step goal is set at 20 steps for demonstration purposes. In production, it could obviously be much higher, usually around 10,000 for most people. We track steps at the window start for calculating steps per period. The last activity calculation timestamp, the current display mode, and whether the goal has been achieved. So next is our main loop. Inside the main loop, the first checks is for the button press. So if the button underscore flag event is set, we increment the mode and use the modulo 3 to cycle through the 3 modes, so 0, 1, and 2. We immediately reset the button flag so we don't press the same press twice. Based on the mode, we display different colors. So mode 0 is blue, mode 1 shows the green mode, and mode 2 shows the red mode. This gives the users manual control over the LED display, and perhaps for different workout types or just personal preferences. And then we write the color to the LEDs and print the mode change for debugging. So next is the activity calculation. So every 5 seconds, we calculate and respond to activity levels. This is just coring the tracking of it. So we have our timing. So we use our time.ticks underscore different to check if the 5 seconds have elapsed. This is more reliable than simply comparing timestamps because it would handle the timer wraparound. Next is the step calculation. And we get the current step count and subtract the steps at the window start. This gives us steps in just this 5-second period, which is our activity metric. And then we update the window start and timestamp for the calculation. If we haven't reached the goal yet and the current steps exceed 20, we trigger the celebration sequence. We set the goal flag so this only happens once, and then print a message and notify the connected BLE devices by updating the goal to 1, which is displayed on the NRF Connect. And then our activity-based feedback. So this is the activity classification. So if the steps in the window are less than 2, means we are inactive, and we play a low 500 hertz tone for 200 milliseconds, and that sets the LED to blue and assigns it to mode 1, the color code 1. So this is more just so of a notification that your activity level is low, sort of just a reminder basically. And then if steps are between 2 and 6, so our green mode, this is our moderate activity level. Our green LED is set and our mode color is in 2. There is no sound here to avoid annoyance during normal activity. And then if the steps exceed 6, that's intensive activity, and we play a high 1500 hertz tone, flash red rapidly using our flash function, and then set the LED to solid red with the color code 3. Next is broadcasting. So we fill the LED strip with the determined color and write it, and then we broadcast both the total step count and the LED color code via BLE. This means the connected apps see real-time updates for both metrics. And then finally, we print a summary for debugging. So that's the steps in this period, then our total steps, and then the current LED color. At the bottom here, we have our entry point and the graceful shutdown. So the if underscore name is equal to our main check, this ensures this code only runs when executed directly and not imported as a module. The exception handling, the try except block catches the keyboard interrupt, which allows users to stop the device with Control C. And then this is just more cleanup. So in the exception handler, we first try to play the shutdown sound. If this is interrupted, we silently pass user experience is then completed, and then we turn off both the LED on pin 22, the on LED, and the RGB LED strip by filling it with black and writing. This ensures the device doesn't stay lit after stopping. And then finally, we print a friendly shutdown message. This cleanup is important for polished user experience and just resource management. So that is the complete walkthrough for my FitBand. To quickly recap the key components, we have the interrupt-driven step detection using the BMI 160 accelerometer, real-time activity classification with visual LED feedback and some audio cues. We have user interaction through button mode switching and Bluetooth low energy broadcasting for the smartphone connectivity on NRF Connect. All this code demonstrates important embedded systems concepts such as the hardware interrupts for efficiency, the I2C sensor communication and BLE service architecture, and multi-sensor user feedback. This project shows how multiple IoT devices can work together to create a functional and interactive wearable device. Thank you for watching, and if you have any questions about the implementation, feel free to ask. Thank you very much.
Hello and welcome to my demonstration. This is my smart wearable fitness band, which is an IoT device that tracks steps, provides real-time feedback with lights and sounds, and can broadcast data over Bluetooth. When I power on the band, it will play a Bluetooth melody and turn on the status LED to show it's active. We'll turn on this LED to show it is on, and this LED will show activity levels. The accelerometer detects steps using interrupts. Each step is counted and stored in real time. I'll simulate a few steps now. So boot up sound on. Now every 5 seconds you will hear a beep. That is for demonstration purposes for the activity level. So usually you would just receive a beep at any period of time you want to set it at for the duration to remind you to be active, because currently in blue you are in inactive mode. What I will demonstrate soon is green, which is active mode, which is just a steady number of steps, and red, which is high intensity, and it will send out a warning sound and it will flash red to just tell you to calm down. But you can set these parameters to whatever you want them to be. So currently we are inactive, and as you can see here, the steps we've done this period is 0, the total is 0, and the LED being displayed is blue, so 00255. I will now display active, so I will do 4 to 5 steps just to show activity levels. 1, 2, 3, 4, 5. Should turn green, and that shows that I am being active. And now you can see that the steps in that period was logged and the total, and then the 5-second period. So this can be adjusted to the user's needs, so maybe for a day, so it can steps in this period and then the total of steps you've done maybe for a whole day. Next I will display high intensity, so it should flash red. And the warning sound. As you can see there, the steps was 8, now the total is 13, and the LED displayed was red. So I have set the step count goal to be 20, so that can be anything for the user. And once it reaches 20, it should give a victory noise and flash yellow. So I'll just steadily increase. So I'm active. Now I'm back to being inactive. And now I've reached my step goal. Shows I'm active. So step goal has been reached, and the total was 20. Currently we are active, and you can toggle through the modes using this push button here. So currently we are in blue. I'll press the button. It has been changed to green, and it means we went to mode switch 1. Press it again, mode switch 2 to red. Press it again, mode switch 0 to blue. This can be used if a user wants to tailor themselves into any activity level. Next, I'll display how I implemented Bluetooth with a step count goal, amount of steps, and what mode the user is in. The band uses BLE to broadcast step count, LED status, and the goal progress. I'll now show this using the NRF Connect app to show the live data being updated. I'll now connect to the FitBand. As you can see here, 3001 will be our step count, 3002 will be the current mode we are in, and 3003 will be our goal, our step goal. So as you can see here, we're receiving 18, the value being 1, which is in our mode 1, and our step goal not yet being reached as we are in 18. So now I will increase the steps to reach our step goal and display our step goal being reached and our mode we are in, and now our value of 20. Here is the shutdown of the device. Stopped by user.